This lesson is entirely about DFT properties. And I've got them listed on that handout sheet. We're only going to be talking about one. Circular convolution. Before we talk about circular convolution, we have to talk about circular shift. And then last, we'll talk about linear convolution using DFTs. And before we dive into the meat of the lesson, I have to give you the broad overview that the reason why digital signal processing exists is because of DFTs. It lets us do operations on digital signals incredibly fast using the FFT algorithm. What in particular we do to our signals is linear convolution. Unfortunately, DFTs natively don't do linear convolution. They do this weird thing called circular convolution. So much of our lesson is going to be about how we can back out a linear convolution that we want from a circular convolution that we don't want. And before we talk about circular convolution, to understand what that is, we've got to talk about what circular shift is. And before we talk about what circular shift is, going still further back in the rabbit hole, we have to talk about what a delay in time does to the DTFT. So big picture, DTFTs work on any kind of discrete time signal, x of n, and they often don't begin at time equals 0. If here's our x of n, then Kevin, what can you tell me about its DTFT? Looks like x e to the j omega, but there's something unusual about this DTFT for this particular x of n. What would it be? This x, the DTFT in general is complex, but it won't be for this x of n.
I honestly don't know what you're asking, sir. So I don't know.
Sure. I'll ask the question a little bit more clearly. In general, the DTFT is complex. And in general, the x of n's that we give you are all real. For this particular x of n, it's got a symmetry.
Right, it's even.
It's even. And so what does that mean for the DTFT?
Would it just be a...
It will no longer be complex. It will be...
I'm sorry, sir. I'm just out of it this morning.
Yeah, sure. It'll be real. So an even in the time domain goes to a real DTFT. So here's a little quick review on symmetry. Now, Jeremiah, the difficulty with this, with DFTs, is that the DTFT is hand calculated, so we can have x of n's that have both positive indices and negative indices. But the DFT, we can't hand calculate. The DFT is something done by MATLAB. And MATLAB always just assumes that your first sample begins at time equals 0. That's what DFTs do in general. You can compute the DTFT of an infinite length x of n, but the DFT computed using the FFT, it's always finite length, and it always begins at n equals 0. So what does that mean for a real DTFT? We can't have our x of n, we can't have it being even anymore, because for DFTs, we're always talking about finite length signals that begin at n equals 0. So you can't have stuff on the left half plane to make it even. What kind of symmetry does an x of n have to give us a real DFT?
Even.
Well, it's not even, because remember, even requires the stuff for negative n to look the same as the stuff for positive n. But I just said that the DFT is finite length, so that there's nothing over here. Can't have things at x equals negative n. We're going to begin at n equals 0 and just go to the right of it.
Does it have to be periodic conjugate symmetric?
Periodic, that's what it's got to be. So it's going to be periodic conjugate symmetric, which for a purely real sequence is just the same as saying it's periodic even. They just use the lingo of periodic conjugate symmetric. Okay, armed with that quick review, what does the delay in time do to a DTFT? If our original signal looks like this for n goes from -2 to +2, and this is our x of n. Now we've delayed, and we know what its DTFT is. I'm not going to calculate it. You could throw it in that summation, but we just know it's equal to x of e to the j omega. Now we're going to have a new x of n minus 2. So that's delayed by 2. And my question is x of n minus 2 can be transformed into the same DTFT as before was transformed, but times what? Jeremiah?
Times e to the, or negative e to the j omega.
Yeah, e to the negative j.
Or e to the negative j 2 omega.
2 omega, that's it. And so you can see that the magnitudes will be the same. The magnitude of this whole thing is equal to the magnitude of the first times the magnitude of the second. The magnitude of the second is the magnitude of 1. So the magnitudes are equal by delaying it, but the phase sure changes. And that makes sense. So that's what's going on for this DTFT. But now my question is, what is the delay for a DFT? You already said over here that you can't have stuff over here on the left, and we don't want to change the finite length nature of our signal. So we can't have a delay because that would either change stuff from where it's in the forbidden zone out, or it would change the length of our signal if we're in the okay zone and pushing it further to the right. So instead we have a circular shift. And a circular shift is what it sounds like. It's easiest to show it, I think, with just a sequence. If here's our original signal, always indexed at 0, and if that has a DFT of capital X of k, right? The DFT is just another sequence. Gordon, how long will the sequence be? Will the DFT be? How long will X of k be if it's the DFT of this sequence?
Infinite.
No. No, you had this the last couple of lessons ago too. X of n is finite length. How long is X of n, Gordon?
It's a length of 4.
It's a length of 4. So that means its DFT has to be a length of 4. You're getting the DFT confused with the DTFT. The DTFT is a continuous function of omega, and it's infinite length. The DFT is a finite length sequence, same length as your input. It's just a sampled version of this, where you sample this between 0 and just under 2 pi. And the power of the DFT is that you can represent it with a finite length of samples right in MATLAB. So it's just like your original signal. This takes up 4 memory spaces. The DFT takes up 4 memory spaces. The DTFT would take up an infinite number of memory spaces, so it doesn't lend itself well towards computation, towards MATLAB computation. All right, so if we circularly shift our input, the circular shift of this by 1, as an example, would shift this 4 circularly back to the beginning. And it would look like this. And our X of k, its DFT, would be equal to the original non-circularly shifted signal times e to the minus j 2 pi k over n, and then times -1, where if it's circularly shifted to the right by 1, that's our -1 here. And that's the same equivalent as the delay for a DTFT. So in general, a circular shift, and this is how we'd write what our circular shift is. Remember our modulo notation. where the angled brackets means we're going to add or subtract multiples of n to whatever in the angle brackets, so that a resulting index will vary somewhere between 0 and 1 less than capital N. And this will have a DFT equal to our original DFT times e to the minus j 2 pi k over n times n naught, where that n naught is the same as that n naught. And notice how similar that is to what we said for the DTFT, where it's equal to the same DTFT. We're just going to multiply it by a complex exponential that's been delayed by some amount. So this is the DFT property for circular shift. Okay, Fawaz?
So the n naught is specifically the time shift, right?
That's right. The circular shift, yeah. This n naught over here is the same as this n naught over here, which is how much it's been shifted. Any other questions about this before we get into the toughest part of the lesson?